30 minutes plus 5 minutes for questions. Edward.
Okay, can everyone hear me all right, like this? Good. Okay, well, thank you very much all for coming. So today I want to tell you about some work, just kind of an offshoot of some longer program now, in conjunction with Rajesh Gopakumar, Matthias, who's here, Shoda, who'll be here soon, Rishabh Kaushik, and Dimalia Sarkar. So the idea today is to try to go back to a very old idea due to 't Hooft, which is basically now 50 years old. And the idea of 't Hooft was to somehow try to see how are large N gauge theories secretly string theories. And the picture he had, if you want, he proved the ADS-CFT correspondence by squinting. This is proof by squinting. So what you do is you look at the Feynman diagrams of the gauge theory. And the idea is that if you start with an expansion of observables in terms of Feynman diagrams, he recognized that the power of n with each diagram corresponded to the Euler characteristic, the genus of the diagram. And he recognized that as the topological expansion of some sort of dual closed string. Making this idea precise, it's been now 50 years, is sort of the hard part. So if you want the whole point of today is trying to find some sort of toy model. And for that, what we're going to do is we're going to look at some topological subsector of n equals 4 super Yang-Mills, where we're going to be able to implement this precisely. Okay? So I'm done with the slides. This was just to give you a bit of a flavor. So this is truly, prescient pictures from 1973. And what we want to do today is to look at a gauge theory. If you want, what we're going to do, we're going to cheat a bit, and we're going to set all the spatial dependence of the Feynman diagrams. We're going to erase that. We're going to want, if you want, not just set h equals g equals c equals 1. We're going to set the propagators to 1. Okay? And what that means for us is that the gauge theory is going to reduce to a simple matrix integral. So you might be familiar with this in computing certain correlation functions in the half BPS sector of n equals 4 super Yang-Mills. Another way of thinking about what I'm talking about today are sort of two-point functions of multi-trace operators in the chiral algebra of n equals 4 super Yang-Mills. So, and if you want, you can just think about this as a matrix model. So let me introduce you the model that we're going to be looking at today. It's a very, very simple integral, just over 2 times n squared variables. So these are over 2 matrices k and m. They're n by n. In this case, they're Hermitian. And they have a very simple coupling, just trace km. And if you want all the interactions of this theory, we're going to be thinking along those lines perturbatively around the free point. Okay? So if you want all the interactions today, what we want to do is we're going to think about those in perturbation theory around the free theory, and we want to understand the string dual just to this free theory. Okay? So let me try to start by telling you what the main result is. So what are the, if you want, gauge invariant observables of this theory? Well, they're going to be correlation functions of the traces of k. So let's say k to the nj. And correlation functions of trace of m to the li, sum over I. So this would be some L plus L point function. And what I can do is I can compute this in this random matrix theory, and I can expand it in a power series of 1 over n. And if you want, what I can do is I can look at a particular coefficient, the coefficient of n to the 2 minus 2g. So I'm just looking at one particular coefficient in the genus expansion. And the statement is that I can compute this via dual closed string theory that we're going to derive today. And this dual closed string theory, what that is going to be a sum over 2D surfaces of a particular genus G. That's the same G over here. And I'm going to tell you about some vertex operators. Let's say nj. Okay. 2 types of vertex operators, li. And this is going to be, and if you want, the dual closed string. So if you want to kind of put these things in your mind, maybe a good thing to think about is this sort of plays the same role as n equals 4 in just this very sort of baby toy model example. And the dual closed string theory we're trying to derive would be like type 2b in ADS5 cross S5. And for us, what's going to play the role of an ADS is going to be very simple. It's just going to be a sphere. So this is the statement that, in particular, this is a statement to every order in 1 over n. So this is not just about the planar limit of the gauge theory. This is about understanding the full 1 over n expansion of the gauge theory and understanding the genus expansion, that as a genus expansion of the dual closed string. So I want to make two comments about this result. So first of all, kind of what's new. So people have been doing matrix models since the 90s. You would think with such a simple matrix model, there's probably nothing that you could really do that's interesting. Let me just try to make one comment. So of course, people had this idea. They tried to flesh out this idea of 't Hooft and think about the relationship between the Feynman diagrams and the 2D world sheets. But if you want, the picture was that if you don't squint hard enough, there's still a bunch of holes in these Feynman diagrams. They're not really 2D surfaces. So the way that you think about it is you think of it as some sort of discretization of the 2D surface. And you need to take a particular further scaling limit, which was known in matrix model days as the double scaling limit. Okay? This is a sort of limit where the Feynman diagrams gets very, very dense. There's lots of vertices. And if you want, you're kind of filling up the holes of the Feynman diagram to give you something like a 2D world sheet. The real reason we're trying to, if you want, the whole conceptual novelty of this talk is stepping away from that double scaling limit. And the reason why we don't want to do that is because we want to study the standard 't Hooft expansion. Okay, so the other examples we know of gauge string duality, they don't have this extra double scaling limit. So if we really want to understand sort of the inner workings of this mechanism, we need to understand how to work in the conventional 't Hooft limit today. And I'll also just mention that there is a sort of open string picture of everything that I'm saying today. So these gauge theories, of course, nowadays, the modern understanding of these gauge theories is that we think of them as some sort of open strings on D-branes. And that's also true for the matrix models here. Okay, so there was a lot of beautiful work by Dijkgraaf and Waffe in the early 2000s that showed that in this very simple setting of topological strings, well, simplified setting of topological strings, you could actually reduce the whole system, the whole open string field theory, down to these very simple matrix integrals. So if they seem too much like toy models to you, just imagine them as open string field theories, and that should scare the living hell out of you. So, good. But if you want, what we want to do today is to really understand, if you want, the closed string picture of this. Okay? And in particular, we want to supplement this by this dictionary of being able to probe this correspondence with observables. So that every time you put in trace k to the n or trace m to the l in this little matrix integral, you know exactly what to do in this dual sum over 2D surfaces on the closed string. You have a question?
If you look at n equals first appearing mill, so you do need the type of double scaling limit to get something like a worldsheet, which is classical string. You need to take lambda to be large, otherwise it's a quantum surface.
We don't. So there is a string theory for any value of lambda, in particular even at lambda equals to 0. The nice bulk description, the classical GR limit, that's in the strong lambda goes to infinity limit. But there's a dual string theory at any value of the 't Hooft coupling. So in particular, we're working in a similar regime as to what Matthias was talking about today, which is expanding around the free gauge theory. Okay, so.
Conceptual questions to the end. If it's
Yeah,
a question about an
ask
index or something, we can ask now, but otherwise.
Yeah, sounds good. Okay, very good. So the first things I need to do to sort of explain this result to you is to do two things. I first need to give you a bit of a new picture as to how the Feynman diagrams are going to realize these 2D world sheets if it's not just via discretization. Okay, if we're stepping away from this limit, we need some new tool to translate between the ribbon graphs of the gauge theory and the world sheets of the dual closed string. And the second thing I'm going to need to do is to then tell you what the dual closed string theories are. Okay, so that's what these first two boards are going to be. So what is kind of the mathematical tool that's going to help us here? It's something that's known as the Strabel parametrization of the moduli space of Riemann surfaces of genus G and n-marked points. So this would be genus G correlators with n-point functions in a string theory. And then there's these extra positive n numbers that are kind of hanging around. So this Strabel parametrization is roughly due to the kind of mid-80s, roughly, so it's somewhat new from a math perspective. And what it does is that it establishes an exact equivalence between metrized ribbon graphs. So these ribbon graphs are really just the gauge theory Feynman diagrams. Okay. Metrized means that we're going to assign a particular length to every edge. Okay. And over here, these are going to be 2D world sheets. Okay. So more precisely, these are really points on this moduli space mgn times r plus n. Now, I'm assuming that most people have probably not really seen this Strabel parameterization, so let me just kind of give you 3 other extra entries in this dictionary to help you kind of keep track. So there's a genus that we can assign to these graphs via v minus e plus f, so the number of vertices minus the edges plus the faces, define some genus, and that's going to be the same as the genus of the world sheet. Okay? So in particular, we're not just going to be looking at planar diagrams. We could look at diagrams of any genus, and those would be capturing the further 1/n corrections in this duality. The other thing to say is that here if we have n, so this n is sort of the number of insertions, okay? Say a vertex operators on a closed string. Okay, so in this case we have 1, 2, 3, and 4. This would be some genus 0 4-point function we're computing. That corresponds to graphs that have 1, 2, 3, 4 faces. So here the number of faces is equal to the number of insertions over here. Okay. The final thing to know is roughly, okay, so how do I really pinpoint what exact 2D surface am I talking about? So imagine you had some torus and you wanted to know what is sort of the tau and tau bar of that particular torus. So the moduli of the surface, how is it captured via this graph? This just looks like a bunch of discrete combinatorial data. Well, it's basically from the lengths. So if you want, the thing to remember from here is that the lengths on these edges are essentially coordinates on moduli space telling you which 2D surface we're talking about. Okay, very good. So this might seem a bit like a bunch of math mumbo jumbo. So let me try to paint maybe a bit more of a physical picture. In particular, I think it's a very appealing picture for those who think in terms of ADS-CFT, thinking a bit about in terms of string bits and maybe spin chains. So what is physically this Strabel construction? So essentially what it does, so what I've done over here is I've redrawn this same 2D world sheet. It's this genus 0 world sheet. It has sort of 4 external insertions. These are sort of the asymptotic closed string states. Okay, they're just related here via some conformal transformation. And what I've done is I've sort of superimposed this graph on top of this world sheet for you. So how does the graph sort of tell you about the world sheet? Well, essentially what it does is that it's writing down the world sheet as a bunch of half-infinite cylinders that are just glued together in a particular way, and they're glued along this graph, okay? Sort of half-infinite cylinders glued along what this graph is called as the Strabel graph. Okay. So here you can see we've just taken these 4 cylinders and we've glued them along the red surface. But in fact, it does a bit more, okay? So what it does is that it in fact actually writes the world sheet as a collection of strips, okay? And I want you to think of these strips, well, in 2 ways. So either, if you want, they're the world sheets of the open strings that made up the gauge theory, and if you want to do, we're gluing together all of these open string world sheets together to form a closed string surface, very much along the lines of this Hegelization program. Another way to think about it is sort of if you want, the world sheet of various string bits. So let me try to show you where these strips live, okay? So if you want, above every edge, okay, you actually kind of break up a half-infinite strip, okay? So the way that this closed string is going to be made out of is going to be made out of 4 strips. So there's the first one over here. It's kind of the one in the back. Okay, if you want. Okay, so I knew this would maybe be a bit confusing, so let me just try to look again at this closed string cylinder diagram. What these 4 strips are basically the 4 strips that I've drawn over here. Okay, so you've taken these 4 strips and you've glued them together. You should think of this, ultimately this is going to be created by a trace of a matrix, say trace m to the 4, and there will be these 4 strips that build up that closed string, okay? So if you want, that's kind of the final thing why I think this is sort of interesting, is that this is some sort of covariant description of a string bit language, sort of string bits, okay? And in particular, sort of the world sheet of each of these string bits, they can come together and they can interact. So we can do much more than the cylinder. We can do any genus G-Riemann surface, okay? So if you want, ultimately the closed string is just made out of these particular bits. Okay, any questions about this? Okay, good. So the second thing, so this, what it was trying to give you a way of thinking about how these Feynman diagrams really could be some sort of genuine 2D surfaces. Now what I want to do is to tell you what closed string theories, what sum over closed 2D worldsheet is it that we're actually capturing, okay? And what's nice, if you want, is that we're going to be able to write down essentially a Lagrangian where e to the s gives exactly the weight of the surface, and that weight is the same as the weight of the Feynman diagram. Okay, so that's kind of the nice thing. So if you want, we've started kind of from the stupidest gauge theories over there. So we're going to get the silliest strings out of it. And in fact, because they're so simple, they actually admit equivalent descriptions, okay? So I'm going to actually talk about 3 equivalent ways of writing down the same closed string theory. So I don't want you to get confused that all of a sudden there's more closed string theories in the game. This would still be like type 2b on ADS5 cross S5. It's just different ways of formulating the same closed string theory, okay? So A is for A model, okay? So this is for an A model topological string, and it's very closely related to the proof of the ADS3 CFT2 correspondence at the free symmetric orbifold point. So it's again going to be this SL2R Wessel-Witten model. We're going to do 2 things extra. So we're going to make a U1 coset out of it. It's still at this very supersymmetric special level of k equals to 1. And one further thing that we do is, because this is much simpler than the symmetric orbifold, we do what's called the A-twist of this worldsheet theory. So this worldsheet theory is much more topological than the standard Wessel-Witten model. Okay, great. The second one, B, stands for B model. You can see where C is going. Yeah, okay. So there's a B model topological string. And here, if you want, the question is, so you give me a matrix model, and I need to tell you what this topological B model is. And if you want, it's what's called a Landau-Ginzburg model. Okay. And to specify this model, all I need to do is to write down a superpotential on the world sheet. And it turns out it's very simple. It's just this 1 over z. And that completely specifies which B model string I'm talking about. So C is for the C model, okay, which does not really exist. So this is the C equals to 1 string. This is a 2D string theory consisting of C equals 25 Liouville and a compact boson at the self-dual radius, compactified at the self-dual radius. Okay. So if you've seen some recent talks about 2D string theory, this fits into that. So all of these string theories, what they're doing is they're essentially the closed string dual just of this topological subsector of n equals 4 that we're talking about. Now, because there's 3 of them, it turns out that when we try to derive this sort of baby version of ADS-CFT, we kind of fall on, depending on how we try to prove the correspondence, we kind of naturally fall on either 3 of these descriptions. So the one that I'll mostly be talking about today here is kind of the naturally connects with the Feynman diagrams of the matrix model. And because of that, this is the one that's going to essentially implement this kind of 't Hooft picture. So that's the one I'll be focusing on today. But I'll just mention these kind of just for the fun of it. So over here, this is derived by something called topological recursion. So people who maybe work in matrix models have maybe seen this. This is sort of classic tool in matrix model theory. And over here, this was actually derived via integrability. But I was a bit too afraid to talk about integrability at this conference over here. And if you want, the idea is that the generating, what was known since the 90s, is that this C equals 1 string theory was completely solvable. And the way it was solvable was that if you looked at the generating function of, so it has 2 types of operators if you want. Okay, so these Tn's and T minus n's. And you look at the generating function of all possible correlators in this C equals 1 string theory, it turns out that this is a tau function of 2D tota. Okay. So this was also something that we used to actually identify the C equals 1 string. Okay. And what's interesting is that this tau function actually had a rewrite in terms of some matrix model that is not actually the matrix model that I talked about today, but would be more something akin to like open strings on giant gravitons in n equals 4. So it's some sort of different open string description that somehow naturally falls on this integrable hierarchy. Okay, very good. So what I want to do now is to, if you want to try to understand, go back to these correlators and try to tautologize this correspondence. Okay, why is it that these correlation functions are being captured by some sort of vertex operators in this dual closed string? The dual closed string that we're going to be focusing on is this Western-Witten model. And the thing to remember, essentially, the only thing you need to know, and Matthias was already mentioning this, is that this worldsheet theory, what it does for a living is that it takes a worldsheet and it wraps a sphere, okay? The worldsheet is just going to wrap some target space sphere, the target space sphere being, again, like the ADS, and it's going to localize to those covering maps. So we want to basically take those correlators and understand how those covering maps are going to come out of them. Okay, very good. So, and I want to kind of tell you this story in 3 parts. So the first one is that we're going to be trying to understand how these diagrams do 2 things. So first of all, how is the diagram going to reconstruct the worldsheet along the lines of what we just did? If you're anything like me, you probably need some example. So we're going to do a simple example, and we're going to look at the simplest Feynman diagram that you could imagine. And then what I want to do is to not only tell you how this diagram reconstructs that 2D surface, but also tells you about how that 2D surface is embedded in the target space. Okay. Now I can take some questions, actually.
There is this Costello Gaiotto. So I understand that your sector is the same as the chiral algebra sector. It's even less.
It's a further subsector of the chiral algebra, exactly.
So you will comment on the relation with the, I think, B model on SL2C or something like that?
Yes, so if you want this, what this computes are actually just multi-trace 2-point functions of this chiral algebra. It can be sort of shown via further twist, if you want, of the chiral algebra. So you get rid of the holomorphic dependence, you do one more twist, you get just basically the Wick contractions of the matrix model. This story, if you want, is kind of the A model. So it's A and B model are related by some symmetry called mirror symmetry. This is kind of the A model story of twisted holography in this subsector. So one of the things, of course, we're working on is to try to lift this to the full chiral algebra of n equals 4. That's kind of the talk, hopefully, in 2 years, if that works out. Okay, does that answer your question? Great, thank you. Okay, so let me try to tell this story. So first of all, as seen, if you want, from the worldsheet. Okay, over here, as seen from target space. Okay, and then here we're going to try to tie these 2 perspectives together. Okay, good. So let's start. So I want to look at the simplest possible correlator just to try to illustrate. So let's look at, say, trace of m squared, trace of m squared, trace of k squared, trace of k squared. And I'm going to restrict here, just for simplicity, to planar diagrams. Okay? So how would I draw this? I would draw basically 4 external vertices. Each of the external vertices have 2 legs, because this is trace m squared. Okay, so this is, say, a k and an m, k and an m. And so one of the possible Wick contractions is going to be this very simple diagram like this. Okay, so this is one contribution. And what we want to understand is how this Feynman diagram, which is very sparse, so it's in no way some sort of good discretization, is going to be dual to this sort of genus 0 4-point function on the strings theory side. Okay? So how do we do this? So first of all, note that here this diagram just has 2 faces. And I told you earlier that there are sort of as many faces in this Strabel graph as there are insertions on the dual side. Okay? So we have to do something that's a little different from the Strabel graph. And so the first lesson that we learn is that the Strabel graph is actually going to be equal to the graph dual of the Feynman diagram. Okay, so try to let me draw that. So we draw the graph dual, so faces go over to vertices. Okay, and now I'll have this type of graph over here. Okay. So let me try to draw again this Strabel graph on that world sheet for you. Okay. okay? Just so that we remember kind of how this is working. So if you want, this is kind of the Strabel graph directly imposed on this 2D world sheet. Now, to really understand which 2D surface we're talking about, the graph isn't enough. Remember, I need to give you the coordinates on moduli space, which are the lengths that I assign to each of these edges. So how do I assign lengths to these edges? Well, that's a bit of an art, and we've tried many things, but sort of the thing that kind of ended up working out is that the lengths, okay, are going to be equal, so we want to assign some numbers to these red lines. It's going to be equal to the number of wick contractions that the red lines are crossing. Okay, so it's the number of wick contractions that it crosses. Okay, so why am I making a fuss about this? Is that the number of wick contractions is always some integer, okay? And remember that the coordinates on moduli space are given by these lengths. So what we're finding is that we're actually finding integer coordinates on the moduli space, okay? So let me try to draw how I imagine the moduli space. I'm French, so you can see there's some, this kind of looks like France for me. Okay, so the moduli space is French. French people always invented everything, right? That's how they think about it. So this is the moduli space. So we're going to be looking in particular here at M04 for us. And each of the Feynman diagrams, we take its graph dual, we assign these lengths, and they're going to be given by a particular point on the moduli space. Again, so the slogan of today's talk is one Feynman diagram is one world sheet. Okay, but each of the points are going to be labeled by these integer coordinates. Okay, so if you want, the picture is not that we're discretizing the 2D surface, but that we're directly latticizing the moduli space. Okay, so that's the main punchline to be taken away from here. Okay, so the punchline is that we've latticized moduli space. Okay. Now, I also made a bunch of fuss about these string bits and sort of gluing open string strips together. So let me try to show you where those are hiding. Okay. I've got another, 10 minutes. Okay. So how is this world sheet built out of 4 strips? So it's going to be built out of 4 strips, and each of these strips are actually just going to be simply the edges of the Feynman diagram. Okay? So we've got 4 edges, and we're going to glue 4 edges together to build this surface. So how are we going to do that? So let me try to bring your attention to kind of this area over here. Okay? So this is sort of this diamond shape. Okay? So where is that diamond shape hiding on the surface over here? It's basically hiding right here. Okay? Ooh. So I'm getting a little overambitious here with my drawing. So I've got something like this kind of happening. Okay. So this diamond shape here is sort of this quarter of the world sheet. Okay, and we've reconstructed this world sheet by gluing 4 different quarters together. And what that is exactly, if you want, the world sheet of this one string bit. So just remember, this was built of, say, trace m squared. Okay. So there's an m and an m that are coming together that are being fused to create this closed string. Okay? So in particular, trace m to the k creates a string of length k, okay, or of k string bits. Okay? So trace m squared gives us a string that is just made out of these 2 bits over here. So this should start looking familiar to some of the spin chain pictures you might have, where single trace operators gives you this sort of nice spin chain, and the number of bits is essential, and the number of spins is related to the power of the matrix that you're taking. Okay, very good. So you might be wondering what possible string theory could ever just localize to these points. So how could I ever have some sort of path integral of a string that is only going to pick out contributions from these very special lattice points? Okay? And this is where we're going to need one more theorem. This is a theorem due to Belly. Okay? And he's basically going to tell us what is special about these surfaces. So if you're a number theorist, you're probably not in this room, but they care about this because they think of these surfaces as Riemann surfaces defined over the algebraic numbers. For us, the reason we like them is that it turns out they are the only world sheets that basically are going to wrap the target space in a very special way. And that way is what's called a belly map. Okay, so this is what's called a belly map. And the reason why this is going to be important is that these belly maps are going to be holomorphic covering maps of a target space sphere branched over exactly 3 points, okay? And what was shown in this SL2R theory at this very special level 1 is that it indeed localizes to these holomorphic covering maps of a sphere. Okay. So what I'm trying to do right now is to try to tell you why is it that that's the string theory we had to land out of from this derivation. Okay. So this is already starting to look good. Okay. So if we find some theory that localizes to these maps, and there's this beautiful theorem that tells us that the only Riemann surfaces that can actually cover the sphere in that particular way are these ones, it's very nice because those are exactly the same ones that we reconstructed directly from the Feynman diagrams. So in the remaining 5 minutes, okay, 5 to 10 minutes of the talk, I want to now sort of tell you not just how to reconstruct the world sheet, but how to reconstruct this embedding map, okay? How to take this, if you want, the string, and put it in the equivalent of the ADS, okay? So that's the next thing we need to do. So what we are looking for is we're looking for covering maps. Okay. Covering maps of a sphere, okay? And they're going to be branched over exactly 3 points. Okay. So let's again take this diagram. Okay, same Feynman diagram. And now what I want to explain to you is how this diagram actually knows not just about this world sheet, not just about the 2D surface, but it even contains all the information we need to reconstruct the map. Okay, so I think I had, say, K, M, K, and M. Okay. So I'm going to take some artistic liberties here, and I'm going to draw a sphere just here as a line, okay? But, you know, it's good to remember that the spheres really look like this, okay? So there's the North Pole, and it has these coordinates x equals to 0. This is x equals to infinity. And let's pick some third point, say x equals to 1. Okay, so x are the target space coordinates, like the ADS coordinates. And what this string theory is going to do is that it's going to be a world sheet that wraps this. Okay, so we're going to so this is our world sheet. And it's going to wrap this sphere. How many times? 4 times. As many times as there are edges of the diagram. Okay, so it's going to be otherwise unramified. Okay, so this is, what do I call it? Infinity. This is x equals to 1. Say x equals to 0. Okay. Now what's going to happen? This world sheet is wrapping the sphere, but sometimes when it wraps, it sort of self-intersects itself. Okay, so it's going to give us a branched cover. And if you want, the way to completely specify this map is actually just telling you how this branching works over each of these 3 points. Okay, so if you're a little ant and you're walking on the top, so what this is, again, this is, say, for us, a genus 0 4-point function. Okay, so it's, again, this world sheet that's wrapping the target space sphere. And so again, this is the target. Okay. And what I need to do is just roughly tell you about the branching over those 3 points. So how does the diagram know about this? Well, we're going to do a little bit of black magic. And I'm just going to pick some orientation. Let's say m goes to k. Okay? And I'm going to draw a number on the left. So let's say I have 1, so m goes to k, 2, 3, and 4. Okay, so, and there are 4 here because it's a degree 4 cover that I'm trying to extract out of this Feynman diagram. And the 3 permutations are going to correspond very naturally to 3 graphical things on these diagrams. So there's going to be, we have 2 different types of vertices. We have the k vertices and the m vertices. Okay, so the k vertices, we've got the m vertices, and the other thing that's natural in this diagram are basically the faces. And I want to extract from this graph some sort of permutations, telling you sort of how the sheets intersect. Okay, so how do I do that? So around this k vertex, I just kind of go around. Okay, so I find some permutation that's going to be around, say, infinity. Okay, say 1, 4. and 2, 3. Okay. I can do the same thing for these M vertices. So this is a 1, 2 permutation and a 3, 4. And then finally, the faces are also again here just given by some permutations. So this was around 0, around 1. So this would be 1, 3, and 2, 4. Okay, so this might just look like a bunch of numbers to you. So let me try to explain what those numbers mean. Okay, so let's try to follow, we're kind of walking along the world sheet and we're on this top cover. Okay, so what this is telling us is that what would happen is as soon as we get above x equals infinity, okay, the north pole of the Riemann sphere, what happens is that we end up on all of a sudden the fourth sheet. That's the 1 and the fourth sheet being permuted here. Okay, and then we can kind of follow this around. So when we're around 1, the fourth sheet kind of comes up to the second sheet, and then finally around 0, the second sheet goes up to the first sheet. Okay. So if you want, I mean, we could fill out the rest of the diagram, but we've got better things to do. Well, yeah, you maybe do. What you can see is that just from the Feynman diagrams, we're able to extract all the information that we need that actually completely specifies this map. So from the Feynman diagrams, we've reconstructed the exact 2D surface, and we've reconstructed how this surface is embedded in the target space. So just in the last 2-3 minutes, I just want to try to tell you how these two things fit together, because they seem probably completely distinct. Okay. And the idea is to go back to the open string strips. Okay, this is, if you want, kind of the most microscopic understanding of how this open-closed string duality works. Okay, so again, remember that these strips are really sort of the world sheets of the open strings that were sort of stretched between the D branes, say the ND3 branes and ADS-CFT. Okay, and what we're going to do is we're going to understand how each of these strips maps directly to the target space. Okay, so one of these strips. Okay. Okay. So I'm just going to map this, if you want, to a strip of unit length. So this has some z coordinates, 0, 1, this is sort of plus I infinity, minus I infinity. Okay, this was our k vertex and our m vertex over here. And we've got our target space. Okay, this is the target. And I'm going to be able to write down the exact map of every single part of the world of these open string strips making up the closed string. Okay? And in fact, it's very, very simple. It's a holomorphic map, and it's just this. Okay? So let's just think about what this map does. It sends plus I infinity to the north pole up here. Okay? So if you want all the insertions of, oh, sorry, maybe I had this other way, m and k. So all the insertions of m, trace m, they create some branching above the north pole at x equals to infinity. Traces of k just are specifying the branching of this map around x equals to 0. Okay. And this open string world sheet, what it's doing, it's just wrapping around the target space sphere once. Okay, so it's doing something very simple. So if you want this whole picture that we have over here of this complicated branched cover of the closed string, one way to understand it is that it's a very, very simple map, just this one. So every edge of the Feynman diagram essentially is a world sheet that wraps the target space sphere once. Okay, so it's a simple map of each open string world sheet. Plus, if you want, this gluing that we did in the first part of the talk, okay, of gluing all of these edges together. Okay, so plus the gluing. So what I'm telling you is that this map over here, you can think of it as a simple map composed with this various gluing that we reconstructed the world sheet. And that's how we end up in the second picture of reconstructing these sort of branched covers of a target space sphere. So hopefully what I've shown you is that there's a way of, if we simplify the theory enough, of looking back at 't Hooft's idea, starting with the Feynman diagrams at the free point, understanding the free theory completely, deriving from it a closed string dual world sheet theory, honestly, understanding how to do that from the Feynman diagrams by first reconstructing the world sheet, and then understanding how these diagrams also reconstruct some covering maps. Now you might think all of this story, there's no way that this could possibly generalize. So I'll point first of all to the symmetric orbifold duality, where there's a sort of similar type of diagram, these are more the Pachman-Rastelli symmetric orbifold diagrams, that also encode these covering maps. And there is a hope that the string dual of free n equals 4 super Yang-Mills would localize to covering maps in some sort of twister space. So that's the real hope that we kind of have, but that there should be a similar story of localizing to these particular points, not these exact ones, but some sort of discrete points on moduli space that again will be the only ones that admit these twister covering maps. So that's the very long-term goal. But I'll stop here. Thank you very much.
Thank you.
Hi. It was a nice talk.
Thank you.
If you consider vertex operators, which is something like trace m to the l, k to the m, without the trace over each of them, can you discuss those kinds of correlation functions?
Do you mean, sorry, traces just in this matrix model, or traces in?
Inside the trace, I want to have a vertex operator which has both m's and k's.
Okay, you caught me. So unfortunately, those words built out of multiple matrices is something that we don't understand. These topological strings don't seem to know enough about that. One reason that I can still get some sleep at night is that these k's and m's, what they end up being in this chiral algebra, are actually operators at different points. So if you want, it's maybe a little unnatural to build traces built out of operators at different points. From a purely matrix model perspective, I agree that that's a very natural thing to do, and in many ways it's kind of the more interesting thing about a two-matrix model versus a one-matrix model. And I don't have anything good to say about it.
That would be like the non-BPS states, right?
Right, so, okay, I could give you some speculation that we've had. In the =1 string, there's a second set of operators that are called the winding operators in the =1 string. Here, the only operators we've captured are these momentum tachyons, so there should be these T-dual momentum operators, and we've tried to work that out a bit, but we're still, we haven't been successful so far.
Thanks for the nice talk. So if you want to add some dynamics into that, because as far as I understood, it's Gaussian, right, model and topological string. So would it be interesting to consider something like fishnet theory, where hexagonization is quite clear, and the graphs you were making is also, I guess, I can draw as well, and this integer modular space. So would it mean that you have to add some topological degrees of freedom of, I don't know, to fill the gaps a bit in between string bits?
Right. So the whole thing, of course, is to try to step away from these matrix models and add, sort of go back to the Feynman diagrams and add some sort of spatial dependence. And the fishnet diagrams are particularly nice because they map to particularly nice points on the moduli space, as you're saying. We haven't got there, but that is something we're hoping that, that might be a further subsector where you might be able to derive a string dual just of that subsector. In particular, just because the graphs are so nice. So if you can figure out kind of what those world sheets are and figure out how to add back the propagators. So right now, the thing that we're trying to do is to understand just this chiral algebra of n = 4. So it's just a free gauged beta gamma system. So it's something very simple like this, trace beta d bar gamma. So these are n by n matrices. And if you want the propagators very simple, it's just sort of 1 over z. So that's our first thing where we're trying to add back some of the spatial dependence. And we're working on it, but I don't have anything concrete to say.
These M and K operators are in some way related with the Oguri-Vav operators of open strings.
Sorry, could you repeat the question?
The M and K operators or matrices are in some way related with the Oguri-Vav operators in open topological strings?
Maybe the Dijkgraaf-Waffe. So in Dijkgraaf-Waffe, what you have is you find that the open string field theory reduces to some holomorphic Chern-Simons. The holomorphic Chern-Simons on CP1 further reduces to, again, the same gauged beta gamma system. And so what those K and M's are insertions of beta at the north pole and gamma at the south pole. So that's what those two operators correspond to.
Just a second. Tiago, can you pass the mic to Arish, please? Thanks.
If you repeat the same analysis for, say, 3 matrices, does that change anything? Like, also, is the target space dimension somehow related to Something like this?
No, so the target space seems to always just be this sphere. And maybe a good way to think about it is that this sphere actually ends up being the same sphere on which say the chiral algebra of n equals 4 is often defined. So if you want, there's a very similar story happening to the symmetric orbifold story where the entire world sheet, what it's doing is that it's sort of localizing to the boundary. And the boundary in this case, in this twisted holography, is the boundary of roughly ADS3, which is again sort of a sphere. So this target space sphere will always just be the boundary. What's going to happen with multiple matrices is to have more branching, more branch points. But the target space will always just be this sphere.
Any other final questions?
Just a quick precision. When you have been describing emerging from the AB and Landau-Ginzburg model.
Yeah, sorry.
Okay, so my question is, do you understand, like a quick point, do you understand how does this can interpolate to Landau-Ginzburg models, as you say, because through the mirror symmetry, like in the case of Suzuki-Kazama, related to perturbed Landau-Ginzburg and equals to Liouville,
Yes.
do you understand how
Yes, so there's of course a whole B model talk I could give you over here. The one-line answer to your question is you take the spectral curve of the matrix model.
Yeah.
There's a polynomial equation for two variables, say x and y, and you solve for x in terms of y, and that spits out the Landau-Ginzburg superpotential.
Okay, and you see this in the fine order description as well?
Yeah, that we understand. Yeah. So if you want, the topological recursion is understood as some sort of Schwinger-Dyson equations in this B model.
Because that would be important is double beta gamma systems as well.
Yeah, that's a good point. That's a good point. Yeah, thank you.
No more questions. Let's thank Edward again.